actually entirely true. I actually rewrote the program from scratch. And I have a poor memory, so it's not because I can memorize the entire thing. All right, so we get to here, go to shared. And then we get to the assembler, which already has the solution from the Tuesday, Thursday, Monday, Wednesday class. Now, obviously, if I see exactly this solution when someone turns it in, I would have a very strong suspicion in that case. Because even though this is one way to do it, doing it exactly the same way is very unlikely. Because I cannot even do it the same way twice. And I've been teaching this class for a while. All right, so the program is in, and then we'll go ahead and to download it. Hmm?
I didn't even notice it was in there.
It was what?
I didn't even notice that had changed.
Oh, yeah. Well, at least I introduced different comments, and the return. The earlier version used register A, to store the return address, and this time I use register B. But in this case, it doesn't really matter because swap has no return value, so we can use register A for that purpose. So we'll go ahead and download CSV to, how should we call it, swap. There we go. It's going to overwrite because I got this already from yesterday. Okay. So now we switch to the command line. There we go. And we'll move it up a little bit so you can see it. Let's see. We are already in temp. Let's go find that jar thing. There we go. So we have all the commands specified here. Run it. Uh-oh, this is not good. Oh, okay, it does work. For a moment, I was kind of thinking, hey, it's not exiting. So maybe the program was not specified correctly. Okay, but just because it exited, doesn't mean that it's implemented correctly. So now we go to the trace analyzer to take a look and find out whether it works or not. So by this time, I'm hoping some people, at least in this class, are starting to use the trace analyzer to get a better idea of what is happening as the program executes, because that can be very useful when it comes to understanding the concepts of this class. Or you can single step, like use Control T to single click throughout the execution of the program. That works too. So we're looking for log.tsv, log.tsv. Stopped and then resumed. So I think I got either a crappy connection or somehow the network is not consistently working. All right. We go, and then we go to analysis. Okay. So if you're very confident with your program, the first thing I would check is to go all the way to the end and make sure the stack pointer is balanced. Okay. So the stack pointer should go back to 0, 0. So we'll go ahead and check that. Huh? Yeah, it is. Yep. Yep, it's still loading. Okay, now it's done. So we go all the way to the end of the, yeah, I think it is not working the way it's supposed to. Nice. Okay, so now I have something to chew on because the program is not working. Yes, yay. Now, okay, so just by scrolling through, okay, oh, come on. So just by scrolling through, do you guys notice anything? it is almost as if the program has a loop. Okay, so but yet the program does not have a loop. So now the first question is, okay, let's find out where the first iteration is. Okay, where did it go back to start the loop? I don't put a halt there. In main, I thought I did, but let's double check, okay? Because I sometimes miss important things like, I would start up OBS, set up the mic, but then I forget to click start streaming, okay? So that's the sort of thing I can do, okay? Not intentionally, okay? But that's the sort of thing that I'm capable of doing. But that's a good idea, okay? Double check first, okay? This is the thing. Has anyone heard of what is Occam's razors? Okay, and what does that mean?
Usually the simplest answer to a problem is the correct one.
Yep, yep. So don't think of convoluted answers. If there are easier ones, right? So that's exactly what it is. Okay? There might be many different reasons why the program is not terminating, but not having a halt instruction is easy. So the program is not working, and so we'll go ahead and try to scan through these lines here. So everything is still working. You can see how the program counter is going forward. So that's all good. Okay, and then at some point, this is going into the swap subroutine, and when swap is done, it's supposed to go back to main. Instead of going back to main, it goes back to location 03. Now, isn't that super suspicious? Because 03 is not a random occurrence. It is the value of not y, but x, right? So I'm returning back to where x, the value of x, okay?
Possibly you overwrote.
No. Well, but we also use that but t is going to have the same value, right?
Well, didn't you store it in register B, your return address?
Yes. So it did use return. So okay. So the nice thing about the trace is you can go back in time. If you do the control T thing and if you don't keep track, when something is overwritten, you don't remember what it was. So the nice thing about the trace is how do we end up at location 3? So this is one way to use the trace analyzer. If your program does not work, this is okay. First of all, how do I know the program is not working? How do I know that it's not supposed to go back to location 3? If you look at the assembler, okay, and the assemble tab is one, it's kind of useful, but it's kind of busy. So the other tab that you can also look into is source debug, okay? So when you look at this, okay, the jump instruction, JMPI instruction, is right here. And the subroutine is supposed to return to the instruction right after the unconditional branch, which is at location 2.1. So I definitely did not branch correctly when the subroutine is concluded. Now, how do I know that the subroutine did conclude? It just did not go back to the right place, because the instruction that caused me to go back to location 3 is at location 4.5. In the assembler, you look up location 4.5, okay? You keep going, and location 4.5 is corresponding to the last JMPB instruction in swap. So swap did complete, okay, without crashing, but it branched to the wrong location. So yes, exactly. We did not deallocate the local variable t. So I was using local variable t as if it is the return address, and it had a value of 3 because it was storing whatever PTR1 was pointing to, and PTR1 was the address of x, and x was initialized to 3. So everything got explained. Okay, but you can also see how the trace analyzer can confirm all of that stuff too, because when you look at the trace analyzer, after the increment, the stack pointer only got back to FB instead of FC. Because the 4 locations, or the locations that should be on the stack, FF is Y, FE is X. FD is the address of Y, FC is the address of X, and then FB is the return address. But when you see D equals to FB, it means it incremented to FB, which means I was using FA as the return address, but FA was the local variable T. So the problem was I did not deallocate the local variable T, causing this particular problem. So now it goes back to location 3, and it's going to execute from location 3 again. So it will consume the stack, okay, because the stack is not rewound correctly. So it will continue to consume more and more of the stack until the whole thing just until the stack crashes into the code and causing the program to just completely go off and die. So is that okay? This is great. I mean, the fact that I accidentally forgot the deallocation of the local variable, causing the program not to work, kind of gave me an excuse to explain, how to debug a program using the trace analyzer. Yep. Go ahead.
Well, doing this assignment made me think about what happens if your program is really long and you start to use a lot of the stack and they crash into each other.
So when the crash crashes into the opcodes, it would not be apparent until it crashes into the opcode that is actually executing.
Right.
So what would happen in that case is it depends on how you crash into that code. Of all the 256 possible opcodes, we have used maybe a little bit more than half of those, which means the other half of the opcodes are invalid. Okay, quote unquote invalid. But all of the invalid opcodes, it all look like the halt instruction, where the microcode is all zeros. In other words, we don't have one single halt instruction. We have a whole bunch of halt opcodes. And every single one of those would do the same thing as what we know as the halt instruction. So chances are, if you crash into the opcode because the stack rules too low, at some point it will execute an quote unquote invalid opcode where there's no current instruction mapping to it. Then it will basically is equivalent to executing the halt instruction and the program does stop. And I think that's what happened in this case because eventually it did stop. Yep.
Does something like this happen on bigger processors?
On the bigger processors, it does not happen like this, okay? So in a bigger processor, you can run out of stack space, and then it will give you a segmentation fault. So a segmentation fault is because in a bigger processor, programs or processes run in what we call protected mode. So when you run in protected mode or a supervised mode, there are many names to refer to it. But when you run in that particular mode, it would say the stack is only from this location to this location. So when your stack pointer goes below that location, not a problem. But when you try to dereference the stack pointer while it is outside of that range, then you have a segmentation fault. So on the processor that you use, on modern computers, it won't happen like this. Okay, you cannot corrupt your own opcode because the stack is growing too low. Now, back in the 70s, when we look at the computers in the 70s, they do have this problem. Okay, the 64K program space is shared between global variables, local variables, the stack, opcodes, and whatnot. So it is possible for a program to crash into its own opcode and have a terrible death in that case. So that's a good question. Yeah.
Multiprocessor, something like this happens on processors like that.
Well, it depends on the complexity of the processor, right? So, just to go off tangent just a little bit here, okay? So we can look at the 6502, which is the processor used by the original Apple II computer. So we can look at this processor, and we can even look for transistor count, okay? So the transistor count there are 3,218 transistors and 1,019 resistors. That's a very low count in terms of transistor count, okay? So now you can look up a modern processor, okay? So we can look up an um, 5 something. Okay, so this is not even the latest and greatest.
It's not 99, 97, 80 or whatever number is up there now.
Yeah, but this is a fairly modest, processor by today's standard. Um,
Transistor count 1.3 million.
right here, 177 million. We went from 3,000 something to 177 million.
How
That's
many transistors are in yours?
graphic.
APU?
Huh?
Is that an APU? Because it says graphics transistors.
The line before that is 382 million.
Oh.
If you,
Yeah,
if you just go to
That
the
one's
beginning
just
of
a
that line.
list of them. It's not.
So let's just say 100 million. Okay, that's pretty safe, right?
Yeah.
So when you compare 3,000 to 100 million, that is still a huge increase.
One is slightly more.
Yeah.
How many's in your toy processor?
Well, I don't know because it doesn't count in transistors. We only have the discrete components. So you can have an estimate if you say, okay, with a multiplexer like this, typically how many transistors are needed. So you can kind of estimate, how many transistors are needed. I can tell you it's going to be more than the 6502 because the way I arrange things is more general purpose than the 6502, which now requires more transistors. Um, but you might even argue and say, but cars from the 70s are not as fast or as safe or as fun to drive as cars today. By that many times, by hundreds of million times, I don't think so. Well, not hundreds of millions, but we're still talking about a huge increase in terms of factor. Um,
Some of these cars are more fun to drive than super modern cars.
that is true.
Because there's that danger factor.
Oh, that's true. Yeah, especially if you don't put on the seatbelt,
Or if it doesn't have a seat.
or it doesn't have a seatbelt. Correct. Yep. Actually, if you want the danger factor, you want the early cars with airbags.
Yeah.
Because if the collision doesn't kill you, the airbag will. You go like, okay, 5 miles per hour collision or 10 miles per hour collision. Bonk. Okay, I survived the accident. You're dead. Yep. There was a video which is kind of funny. I'm not sure whether it's real or not. There was a person driving a sporty car at a crosswalk, and an old lady was walking really, really slowly, across, and then the car honked the old lady. Then the old lady used her cane, and just whack the bumper of the car, and then the airbag deployed. I'm not sure whether it's real or not, okay? Because these days you can never tell. But I don't think anyone is going to be willingly going to put himself or herself in a situation where the airbag is going to deploy.
You're the spot to hit to deploy an airbag.
Yep, you can look it up on YouTube. I'm pretty sure you can find it. It's at least entertaining to watch. It's one of those instant karma thing. Yep. All right. So getting back to our code. Yep.
So just to follow up on the segmentation fault thing. So that's it's the same thing as what's happening with ours, except they just have an error code for it, or
No, a segmentation fault is a very interesting mechanism of the processor. All it says is an instruction attempts to access a location that is not there yet. Okay, because in modern processors there are two address spaces. One is a physical address space, and that has to do with how much RAM you install in your computer. The other one is called the logical address space, which is a lot bigger. It's huge, gigantic, compared to the actual amount of RAM that you have installed. Okay, so how can you now pretend to have like 64 gigs of RAM when you only have installed like say 4 gigs of RAM? Okay, so it's a pretense, right? So the idea is a particular what we call a page in logical memory does not even exist until you say, oh, I need to access that location. Okay, so you'll be accessing logical space location that is not there yet, okay? And then the segmentation fault will happen. So the segmentation fault is a form of interrupt to the processor. So the processor will go like, whoa, wait, hold on a second here. What is happening here? So the processor will now look at the segmentation fault and say, okay, which process is attempting to access which location in RAM in the logical space? If it does work out, like, oh yeah, this program is supposed to have a memory space at least this big, and this is within that memory space, at that point, the processor, running the kernel code of an operating system, will then allocate a physical page in RAM, the actual RAM that you have installed on the motherboard, and say, this chunk of memory is now mapped to this part in the logical space. Now, on the other hand, if you run out of stack space because your program has infinite recursion, okay, then the processor running the kernel code would say, I'm sorry, I'm only supposed to allocate, let's say, 4 megabytes of space for the stack, and you're using more than that. I cannot do anything to help you out in this case. Then the program would actually crash, with a segmentation fault in Linux. So this is way out of the topics that is supposed to be in this class, but it does relate in the sense that you have different memory spaces, and there's a mechanism. Segmentation fault is a mechanism that is really kind of like interrupts, because it's the memory management unit calling the processor and go like, hey, I need your attention here. And then the processor will have, running the kernel code, will have to decide whether it's a legitimate thing or whether it's not legitimate. If it is legitimate, then a page of physical space will now be mapped into that logical space. If not, then it will just crash. So are we good so far? So do we want to rerun this code just to make sure everything is good? I think that's a good idea.
You just have to add the increment D.
Yes, that is the only thing I added here, to deallocate the local variable t. That's the only thing. So we copy the whole thing again.
It's like we're getting semicolon in C++.
Oh, it's worse than that, because in the case of C++, it would just give you a compile time error, right?
Right.
This is a runtime thing, and it does not say anything like, oh, I think you forgot to deallocate.
It's like, but I don't know. I'm going to keep going with the conversation.
That's what assembly language programming is like.
It's like, if you think something's wrong, something probably is wrong.
But it's hard to figure out what is wrong.
Exactly.
But if this is not challenging enough, okay, then it's good to write assembly code in interrupt surface handlers. ISRs, writing ISRs in assembly, that brings a whole new level of interesting debugging. Because interrupts are asynchronous. Okay, so with this problem, okay, the nice thing about the problem that we had is if you run the program again, it would crash the same way. It would terminate exactly the same way. If you run it again, it would terminate exactly the same way. So it's consistent.